So you guys been working on the photoelectric effect, and of course, you have your sort of map things out. You got your piece of metal. The metal has a work function, and we had typically the ultraviolet was coming in, so have some UV light coming in, and then if we had more energy in the work function, the electron would jump off. We sort of mapped things out. We had the photon energy was coming in. The photon energy, and some of that would go to the work function, and then whatever leftover stuff would go to the kinetic energy electrons. It's just finding energies, adding and subtracting them. Now, something else that's really kind of cool that happens with a similar type of effect, except, I'm going to draw another piece of metal here, except what we're going to do this time is we are going to use X-rays. So if we take an X-ray, and of course, X-rays have more power and energy than ultraviolet do. They've got a higher frequency, so more energy. You can have something similar happen where an electron is going to jump off. But when they did this with X-rays, and this happened sort of like in the 1920s, they put an X-ray in, an electron came jumping off, but then something else happened which is kind of strange. Not only did they get an electron coming out of it, but they got another X-ray. They got sort of a lower energy X-ray. So not quite as powerful as the first one. So it's kind of cool because they had the X-ray come in, which has energy, of course, and lots of energy compared to ultraviolet. So electron jumps off, no problem. But then they actually got a second photon coming out the other side as well. And we sort of mapped it out. It's actually like the sort of exact same idea as the photoelectric effect, conserving energy. We still want to have, it's all about the conservation of energy. So of course, the energy of the first photon, so that's this guy right here, and then the energy comes in, and some of that energy makes a second photon, so energy of the second photon, so that we know this is your E2 over here. And then whatever's left over is just the kinetic energy of the electron. And you can do the same type of calculations we did before. You got to do the HF for the first photon, HF for the second photon, get their energies, add them together, subtract them, get kinetic energies. Like, it's all the same type of thing. It's sort of like almost the exact same idea as photoelectric effect, except you sort of switch out a work function with the energy of the second photon, but it's the exact same idea. And why we're not worried about work, we're not going to worry about the work function stuff right now. There's reasons behind that type of stuff. That's just a good estimation of what's going on. We're not going to worry about that. Okay. Now, this is really cool and all that kind of stuff. You got, instead of having, just one photon, you got two photons, you got a new one being emitted, the whole bit. Now, this wasn't actually the big deal about this one. What's a really big deal about this one is if you actually look at the actual general setup where we have something coming in and then two things coming out, well, that should look familiar to you from your momentum type stuff when you look at collisions. We actually have sort of like a collision going on, like a scattering collision. So when you do this, you have like an actual collision occur. If you actually have some kind of collision, what about momentum? And this was a big deal in the 1920s. And it looked like you could actually have collisions and with photons, with light, and they could then have conservation momentum. Of course, what's crazy about this, what threw people off, is how does light actually have momentum? That's just crazy talk. So it was a really big deal. Now, this was done by a guy named Compton. Let's see, Compton. Okay, so this is what's often called the Compton effect or Compton scattering. And of course, the big deal is the whole momentum idea. How can light possibly have momentum? That didn't seem to make any sense. Because if you go to classic momentum, when you guys done like with mechanics, momentum is equal to mass times velocity. And of course, the main problem is that mass. How does light possibly have mass? Well, you have to sort of back up a little bit, and you sort of have to ask yourself a little bit, what is mass in the first place? Now, it's not how much stuff there is, it's not how big stuff is, and stuff. It gets a little more complicated than that. But luckily around this time, just before this, Einstein actually came along and actually defined what mass truly actually is. And of course, some of you guys know this, but mass is actually a form of energy, and that's where the whole E equals mc squared comes from. Now, it's actually part of a much larger expression, but that's the basic one that most people know, although most people have no idea what it actually means. But energy and mass are just different forms of the same thing. Einstein showed this with his relativity expressions and relativity theory. The mass was just a form of energy, and hence nuclear power works by changing mass into energy. And mass has ridiculous amounts of energy. It's crazy concentrated energy, and that's why nuclear reactors, bombs, explosions, all that kind of stuff, nuclear reactions are so powerful. So with this idea, you can take this and you can rearrange this, and mass is going to be equal to E divided by c squared. So in the expression, the P equals mv expression, mass is the problem. Does light have mass? Well, not really, but it has energy, and mass is just a form of energy. So when we do classical momentum, we're dealing with that energy as mass energy to calculate basic momentum. Well, maybe for light momentum, we need to look at not the mass per se, but we need to look at the mass in terms of light energy. So if we take this little expression right here, we can actually substitute for the m. We can actually substitute E divided by c squared times v. Now, of course, v for light is just c. I mean, that's your c value right there, which means this cancels off one of those guys, and we're left with E divided by c, and you can actually calculate the momentum of light, which is unbelievable. And of course, this is the energy, so you could do Planck's hypothesis, hf over c, and f divided by c, that's just the inverse of lambda. So you'll see different expressions for this. And this was the huge consequence and thing that sort of came out of the whole Compton scattering, Compton effect type thing, is you could actually calculate the momentum of a photon. Now, of course, he's got to get away from the idea that momentum is mass times velocity. It's not really about mass and velocity. It's more about the energy and not the mass. Mass is just the form of energy that's being taken by regular common type things. So this is a really big deal. So it was awesome. It was really neat that light has momentum question mark. And not only does it sort of answer that, apparently the answer is yes, apparently. Okay, not only does it have that, but also helps to redefine and connect other things together. You got all these things coming together. You got light being sort of defined as a particle that can have momentum, but also redefining what mass actually is. And mass is just a form of energy, which opens the doors to a whole bunch of other things. So it's really neat. So you had the photoelectric effect, which was a big deal and really showed that Planck was onto something with the particle model of light, with the photon idea, with the bundles of energy, the quantized energy. And then we get to the 1920s with the Compton scattering, that not only that, but not only does light have the particle attributes of quantized energy and chunks of stuff, it takes on another particle-ish type property of actually having momentum, which is really neat. Okay, so this is what you got out of the Compton scattering that was huge. Now, of course, solving Compton scattering, you just want to stick with energy. It's all about energies. You don't really want to use momentum. It gets way more complicated. It's much better to use the energy scalar quantities than trying to deal with momentum. Although you can do it, but it's really neat how these things can actually tie together. So let's sort of clean this up a little bit, and then we can sort of summarize some stuff. And from my regular classes, the lab, we would do some calculations with this, but I just want to get the idea out to you guys and show you what's going on with that. So far we have, you guys have done the photoelectric effect. And of course, that was a really big deal. And it actually definitely showed that actual Planck's hypothesis and the whole quantized energy of photons and that type of stuff. So the photoelectric effect showed Planck's hypothesis, the quantized energy for photons was definitely valid in some way. And then what I just showed you here, we have the Compton effect or Compton scattering, which is again really cool, and actually showed that light actually has momentum, which is really cool. Now, of course, in order to actually do this, this actually applied Einstein's idea of E equals mc squared, and it showed that mass is just a form of energy. Now we can actually take this one step further. Photoelectric effect, typically you are looking at ultraviolet. Compton scattering, Compton effect, we sort of talked about this before. This is typically using X-rays, which are higher energy. If you take this one step further, if you go from, you got the ultraviolet, which is lower energy, you got the X-rays, which is higher. If you go even higher, you actually get a different effect as well, which connects to this type of stuff that really also enhances this right here. If you do the next stage, so to speak, if you use really, really, really high energy photons, you get something else that you can actually do. If you use the highest energy photons, you can do something else. Now, for the high, there's sort of like two things that they actually do. My favorite is something like this. You can take a couple things, and there's two options. We're going to look at two things. I want to show you two things. So one is called annihilation, and the other one is what is called pair production. Okay, now annihilation, what they will do is they'll actually literally smash two particles together. And what happens when you smash the two particles together, they will actually create an actual photon, and the particles will actually disappear. In pair production, you get sort of the opposite. You can sort of smash a particle, or not, it's not a particle, sorry about that. You sort of smash a photon into a target, and you can actually create particles. And both of these things, either one of these two things, these guys are only true and they only work if mass is a form of energy, and you can go back and forth between the two. Okay, so let me show you something that'll like sort of tie this together and show what I'm talking about here. Okay, so this is an image from a bubble chamber, which is used to show the paths of subatomic particles when they move through stuff, and usually they're embedded magnetic fields, which causes charged particles to go in spirals. That's what those are, all the circle things. So if a particle goes through and it's not charged, it's neutral, it goes straight. If it's charged positive, it'll curl one way. If it's charged negative, it'll curl the other way, and depending how fast they are and how big they are, that dictates the actual shape of the path. So that's just an image. So here is an image of pair production. Now, it's kind of hard to see exactly what's going on here, so I've sort of added what's going on. You can see on the left-hand side, a photon came in, and a photon came in, just like photoelectric effect or Compton scattering, a photon came in from the left. It smashed into an electron, and the electron actually goes flying off. That's the scattered atomic electron. And then what happens is the photon actually changes into an electron and a positron. One's negative, one's positive, one curls one way, one curls the other way. So you actually have the photon turning into solid particles with mass. And this is only possible if energy and mass are different forms of the same thing. So it's kind of cool because the photon actually disappeared and actually turned into solid particles. One has to be positive, one has to be negative because they have to electrically cancel out. So it's really kind of cool. So that is what's called pair production. Now, for annihilation, it's sort of the exact opposite. So here's another little picture of pair production. Got the gamma coming in, the gamma turns into the two particles. In annihilation, what they will do is they can take something like an electron and a positron, and they can actually smash them together, and the two particles will actually totally disappear and turn into a single photon. So they'll annihilate the particles. The actual particles with mass do not exist anymore and actually turn into a single photon. So this takes this whole thing way to the highest level, where actually you're sort of destroying matter and you're creating matter, is literally what you're doing, because matter can be created and destroyed. It happens all the time with nuclear reactions. It's the energy that can't be created or destroyed. So you're using pure energy, or energy in its purest form as light, and turning it into matter. And then in annihilation, you're actually taking actual solid metal particles and turning them back into energy. So these are like the highest level type stuff that sort of came out, these cool experiments, and really showed that mass is just another form of energy.